Alright, once again I welcome you to this lesson. Still under buffer solutions. I told you since this is a ionic equilibria, it contributes a lot to physical chemistry. And today, still under buffer solutions, we are going to look at the Anderson-Hasselbalch equation, which equation is used to calculate the questions under buffer solutions. So, we have looked at, in our previous videos, we've looked at acidic buffers and basic buffers, but in this video, we want to see the acidic buffer equation of Anderson-Hasselbalch, and also we are going to look at the alkaline buffer equation of Anderson-Hasselbalch. This one simply means that this was Anderson, this was Hasselbalch, and these people combined and maybe did studies about these solutions. So now, here we are going to come. I'm going to begin with the acidic buffer. I'm going to begin with the acidic buffer. Now, if you consider an acidic buffer consisting of, consider a mixture or a solution of ethanoic acid and sodium ethanoate remember, we said that ethanoic acid is a weak acid in our previous video, and therefore ethanoic acid partially ionized produce ethanoate ions and the hydrogen ions. Then sodium ethanoate will completely dissociate, produce ethanoate ions also, and sodium ions. What does this imply? Since the acid is dissociating or ionizing, we've got what we call acid dissociation constant. So, we look at what is dissociating basically the acid, and being a weak acids have got the acid dissociation constant Ka. Let me call this one equation 1 and maybe call this one equation 2. So from equation 1, the acid dissociation constant Ka, this one means the acid dissociation constant, so it is always equal to the concentration of the ions in the product, so that is CH3 COO minus. These square brackets represent concentration times the concentration of hydrogen ions out of the concentration of what is dissociating. So we have CH3 COOH. But remember, we use this to calculate the pH of these solutions. And to calculate pH itself means the hydrogen potential. So we are looking at the hydrogen ion concentration. So what we are going to do, we have to make hydrogen concentration the subject of this formula. Now, there are those ones like Ziwa you do PCB. So maybe if there are some cases that confuse you, maybe here we do cross multiply. When you do cross multiply, you're going to have your Ka times the concentration of ethanoic acid is equals to, this one will multiply into that, so it will be the concentration of ethanoate ions times the concentration of hydrogen ions. But since we are looking for pH, you take the concentration of hydrogen ions as the subject of this equation. So, our concentration of hydrogen ions is going to be equal to, we shall divide by concentration of ethanoate ions both sides. So it is going to be Ka times the concentration of ethanoic acid out of concentration of ethanoate ions. Now, after doing this one may not, the concentration of hydrogen ions may not easily give you the pH. If you have it, you can take the pH direct. But after having this, when we reach here, we take logarithm of base 10 both sides. So we shall take negative logarithm of base 10 both sides. So my step here is to take negative logarithm to base 10 both sides. So when you take the logarithm to base 10 both sides, let me do like this. If we take the logarithm of base 10 both sides, it means that here we shall have negative logarithm to base 10 of hydrogen ion concentration is equaling to negative logarithm to base 10 of Ka times concentration of ethanoic acid out of concentration of ethanoate ions. So this is the same as negative logarithm base 10 of hydrogen ions is equals to, now when you look at here, we are going to apply some law of logarithms from our O-level mathematics. Even though you are not doing pure math, this one can favor you here. We are multiplying numbers Ka and this ratio of concentration. Meaning we are multiplying numbers of the same base because they are under the same base logarithm of base 10. Implying that since I'm multiplying, I will bring them this side and add. So I will say negative logarithm to base 10 of Ka plus negative logarithm to base 10 of the concentration of ethanoate ions, rather of ethanoic acid, sorry, out of the concentration of ethanoate ions. And this one will give us, when you take the negative logarithm here, negative logarithm of base 10 of hydrogen ion concentration gives us pH. In other words, pH is always equal to negative logarithm of concentration of hydrogen ions. So pH is equals to negative logarithm to base 10 of Ka gives us pKa. So this one will be pKa, meaning that you will be given the acid dissociation constant of that very acid in question, and plus, if, because this is a ratio, you cannot say P something, no. This is a ratio of concentration, and this is a negative. So the moment we want to eliminate this negative and call it a positive, we shall say plus logarithm. The moment you say plus, it means that you've changed the sign here, so also these ones will change the positions. And therefore, we shall have logarithm of base 10 of the concentration of ethanoate ions out of the concentration of ethanoic acid. Implying that at this stage, I can conclude and say that my pH of an acid buffer is equals to pKa plus logarithm to base 10 of this concentration is for the solute because it is from ionization of a solute, and therefore it is, I can say concentration of the solute, whichever solute that will be given, out of the concentration of an acid. And what I have derived for you here is what we call the Handerson Hasselbalch equation for an acidic buffer. We are going to look at its application, or how we can apply this equation in calculations, and we shall be looking at how to prepare acidic buffers in our other videos to come, or in our other lessons. I will show you how we prepare buffers and how we use this equation and how we can work upon it to see that all the calculations about buffers are understood. Miria, thank you for the thumb. I like it, and thank you for appreciating. So let's meet in our other lessons specifically for calculations applying this equation of Handerson Hasselbalch. Good time. Don't forget to subscribe.